Hi everyone, the proof by contradiction. Hello Kirby. I want to show the concentric hierarchy embrace. This is a rhombic tricontahdron and it's enclosing the pentagonal dodecahedron. Inside that pentagonal dodecahedron we have a synergetic cube of 72 modules, and inside of that we're going to put our tetrahedron, which I used throughout this demonstration. The edges prime vector, synergetic prime vector 2, and inside of that we have a octahedron, just regular octahedron. So we have 5 solids in here. Now let me show the sixth one. The sixth one, this is a mite, and this is a part of the rhombic dodecahedron, so we just see that the edge is protruding from a tricontahdron. The reason I do this, so we know we're talking about the same tricontahdrons, and synergetics has 2 tricontahdrons. Now, I want to show also the icosahedron, because I couldn't show it in this kind of hierarchy, but this is a relative icosahedron, relative in volume to the tricontahdron. This sphere is a tricontahdron sphere, 7.5 volume synergetics volume tricontahdron. This sphere is actually a little bit larger than this icosahedron, even though this icosahedron enclosing this sphere. Now on the top of this sphere, I want to use this pentagonal cupola just to show that we have a very good match with these spheres. This is a pentagonal cupola, and we see this is the face of the tricontahdron, and a sphere tangentially touching in these 5 points. Here we have also the surface triangles which are on an icosahedron, and I'm going to put them on a sphere to show that we have a tricontahdron face again, and a sphere touches in these edges in here. Now edge of this edge of icosahedra edge is the edge of the synergetic 72 block cube. You can verify that. All this is very simple and straightforward. The volume to surface ratio is changing with the size of the solid. That's true for any solid. But when solids are in a concentric embrace, just like I demonstrated, the mutual relations remains constant. Sphere triconta ratio is the tricontahdron, 7.5 volume tricontahdron, and a sphere. The ratio of these 2 objects is 0.8872000002. Sure, one can reduce a solid into whatever he or she desires to match, but in this hierarchy we have rules, patterns, and that is, if a solid appears more than once in the same hierarchy, it gains frequency, thus a tuple in volume, which is obviously not true in the case of synergetic triconta. For example, here is the cube octahedron, here are the isotropic vector matrix sphere, and here is the sphere which encloses this vector equilibrium. A diameter of this sphere is the radius of this one. The mutual relation of these 2 is 8. This is 8 times smaller in volume than that. Now in synergetics, if we have, this is the synergetic sphere, if there would be a second triconta, which there is not, there is no reason for it to be there, but if there would be one, the mutual relations, if solids which appear more than once in a hierarchy, would have to be same. In other words, the small tricontahdron, the volume 5 tricontahdron, is non-existent. This tricontahdron would have volume of 2.5 cubes, just like this, or 3 small cube octahedrons, again reduced by half. So this is it, and this is the relationship of these spheres. It cannot be any other way. The 7.5 synergetics volume triconta, this one, is equivalent to 3 cube octahedrons. Now let's say this is a synergetics cube octahedron. It contains 60 modules, A and B modules, so 3 times 60 is 180. So we have 180 synergetics blocks, A and B modules, which are volumetrically, this whole tree of these matches that, but there is only 120 of these T modules in here. That means the A module or a B module have no match unless we would dissect this triconta into 180 pieces. Then we would have a match, but then we have no lowest common denominator. In other words, synergetics has no relations on the outside of this hierarchy. Now let's use our modules. We have 3 cube octahedron also, but my cube octahedron contains 40 blocks, so 3 times 4 is 120. Wow, now we have the same exact match to 1/6 of the cube, exactly. Now I also want to say that this tricontahdron from the center of the sphere to the surface of the sphere is where is that? 7.2811529471. That's the edge of the square. I have a little mark in here which this triconta was built on. So now we have the lowest common denominator. We are on the outside of the hierarchy, and the edges of the rhombic dodecahedron also intersecting with that of the triconta, as I demonstrated. So we contain all the attributes at one location, but not in synergetics. In synergetics they have 2 locations to find all these relations. Unfortunately, they have no relations in either case. To make a match, they reduce the existing sphere by 1.5 and not half as it should be. In other words, they reduce this sphere, this tricontaedral sphere, they reduce it by 1.5, and suddenly they almost matching the synergetics isotropic vector matrix spheres. They match it by first 4 digits. In other words, you can't tell by eyes. The tricontaedral, small triconta sphere is just a hairline smaller, undetectable by eyes. Wow, now so they reduce the sphere, so now it's, hold on. But this triconta has a relative volume of 2 cube octahedrons. This reduced triconta, not 3, but 2. Well, that's a gigantic error, which is also a beautiful synergetics discovery. It's genius. The error is enormous. The synergetics calculations do not match the actual modeling. They match an abstract. This is synergetics numerology at best, far from science or a actual modeling. Thank you all for your time.